Hi, good morning. Welcome to today's session of Computer Organization and Architecture. So in the previous class, we discussed briefly about the assembly language, and in this today's session we are going to continue the discussion on the assembly language. So we saw that in assembly language we will not be using the lengthy keywords like branch or increment, decrement. Okay, instead of that we will be using short words which are called as mnemonics. And also we saw that in order to indicate which addressing mode we are using, along with specifying the operation to be performed, we need to specify the addressing mode which is being used in case of the assembly language. And we know that there is a program called as assembler which converts the source program. So high level program which we write, which is in the text form, is called as source program, that needs to be converted into object program, and object program is nothing but machine level language. And this is done by the assembler. And also we discussed that the set of rules and all the mnemonics grouped together is considered as assembly language. And if you consider only the rules of writing the program in assembly language, is called as the syntax of the program. If you consider rules in any of the languages, it is considered as the syntax of the program. And we know that each and every machine or each and every the instruction what we are going to write that are called as mnemonics, and each mnemonic will be having a code called as opcode. These are all the things we discussed in the previous class. And in today's class we are going to discuss about one more type of instructions which are called as assembler directives. So that will be used in assembly language. Assembler directives are another type of instructions. These are going to be used in assembly level language program in order to perform certain tasks which include reservation of the data and other control functions, and sometimes it is used to give the address and data which is to be loaded. Let us consider the assembler directives and let us see few examples of assembler directives so that we can understand how the assembler converts the source program into object program. In order to understand that, first let us consider the program segment which we had taken as an example for discussing many of the addressing modes. Let us consider the same program segment of adding n numbers, and let us see what is the assembly level language program code for that particular object source program. Let me consider or you can do one thing, let this be R1, let this be R0. Move n comma R1, move hash num1 comma R2, clear R0. After this add contents of R2 to R0. Next add 4 to R0 to indicate the next word. Next decrement R1, branch greater than 0 to loop, where the loop is here. Then yes, so this is the program segment, and let us assign addresses to these. Yes, let me indicate the starting address is 100. Next, since it is a 32-bit computer, let us consider the addresses 104, 108, 112, 116, 120, 124. Yes, so after this we will be having one more instruction, so that is move R0 comma sum. 128. Okay, yes. Next, let us assume, so we have sum, okay, at 200, and let us assume at 204, okay, we have n value, and let us assume n value is 100, okay. And next, let us assume num1, it is at 208, okay, and let us assume num n, okay, at 604, okay, let me assume it is at 604, okay, yes. So now this is the program segment we have, and if you consider, okay, this as the program segment, and if this is to be the object program form, that is, so if the object program after converting from high level language to the object program, so this is the format we want, okay. This sum should be at 200, and the other instructions whatever I have written, so these are the addresses and these are the values of the program, okay. Yes, if this is to be the format of the object program, then we need to write the assembler code, okay, assembly language program, okay, for this, so that it appropriately assigns the addresses for all these, okay, as required. So in order to do so, the assembler should understand, okay, how to interpret the instructions, okay, and how to replace the data, and where to place the data, where to place the instructions which are present. All this information must be known to the assembler. So in order to provide all those information about where to place, okay, how to interpret, and all this will be given to the assembler through the assembler directives or the code, okay. We are going to write one more code in assembly language, okay, and that code will provide the information to the assembler to create object program, okay. Now let us see the assembly language code, okay, program for this, okay. Yes, so if you consider assembly language program for this, yes, so let me write, and here as I said we will be using the assembler directives. Yes, let me yes. Yes, we have 3 columns here. One is label or the addressing information. Next we have operation, and the last is the operand. Okay. So let us write the assembly language program for the program segment whatever we have written. Okay. Yes, sum EQ 200, origin 204, next is data word, is data word, okay, 100 and the label for this n. Next is num1, okay, num1 reserve 400, okay. I will explain what are these later. origin, next label start. Okay, here you will be having start, move n comma r1. Okay, all the instructions will be here, machine instructions. So whatever we have written, so start, move n comma r1 hash num1 comma r2. Next you will be having the label as loop, add, okay, add contents of r2 to r0, then add 4 to r2, decrement DEC. Okay, so DEC r1. After this, okay, you will be having next instruction as branch instruction, and branch instruction is written as B G T Z loop. Okay, next you will be having move. Okay, usually all these are capital letters. Move r0 comma sum, then you will be having return. Next you will be having, okay, end and start. Okay, and in this, okay, code you can observe. So here I have written sum, EQU, origin, data word, reserve. All these are assembler directives. And these are machine instructions. These and, okay, so branch, these are machine instructions that are to be loaded into the object program. And once again, these are assembler directives. Yes. So if you observe, okay, in assembler directives, so we have used label, okay, operation, and data or addressing information. Before that I said operand, that is the, okay, standard form. So in place of operand we have the data, okay, which is same. Yes. So if you observe sum, so we have sum EQU 200 as the first, okay, assembler directive in this case. So operation of this EQU is to replace the name sum, okay, by 200. As I said, all these are, okay, capital letters. Remember, in assembly level language program, so you will be writing the code using all capitals. Yes. So sum EQU 200, when this is, okay, executed, and remember, this need not to be executed and this need not to be present in the object code. As I said, if the object code is to be in this form, okay, then we have to write an assembly code like this. So these are just directives to the assembler to say what to be done when this sum is encountered. It will not be there in the objective program and it will not be executed also. Okay. Yes. Sum EQU 200. So this directs the assembler saying that the name sum is to be replaced by value 200. Whenever the sum, okay, occurs in the program, it will be replaced by 200. See here. So we have sum, so that will be replaced by 200. Okay. Then we have the next assembler directive as origin. Okay. And I have written origin 204. So that actually gives you the information about the address of the next data word. Okay. So which is present in the next statement. So here we have origin 204. So this shows that the following data word is, okay, present at the address 204. And if you observe, we have n data word 100. Okay. So this data word, okay, this directive function is to, okay, store the value of n or the value at the address 204 as 100. See here, so in this object program you can observe, so n we have at 204 and it is having a value of 100. So now if you observe origin function is to indicate the address of the following instruction. So here origin 204 shows the address of n is at 204 and n data word 100. So this is going to write the constant value 100 into the address location 204. And next num1 reserve 400. So this is the next directive we have, reserve directive. It is going to reserve 400 bytes of memory location in or at the starting of the address num1. So num1 is at 208. Starting from 208 it is going to reserve a memory space of 400 bytes in the memory. So that is the function of the reserve. As I said earlier, so you will be having directives which actually performs the operation of reserving the data, assigning the data, etc. So here you can observe, so we have 4 examples of assembler directives. EQU, it performs assigning, it is a straightforward assignment. Whenever we encounter the label or the name sum, then it will be replaced by 200. Origin says, so the next instruction where it is going to start, and origin 204 indicates the next data word, what we have, constant value what we have, it has to be stored at 204. And next we have reserve. So reserve is going to allocate some memory space for the given program. And next we have once again origin 100. As I said, it indicates so where the next following instructions are to be stored in the memory. So origin 100, it says that the following machine instructions must be stored in the memory starting at the address 100. And if you observe, we have start and loop as the labels, and all the other instructions are same as the instructions in the object that is the source program, or the high level program. And next you have the branch, BGTZ. This is the code used earlier while explaining the while explaining the assembly language. I said BR for the branch. You can use BR, or depending on the condition, branch to target if the value becomes equal to 0 after decrementing this. So since we have a condition saying that if the value becomes equal to 0, then it has to exit, and if it is not equal to 0, it has to continue the execution. So BGTZ is used instead of BR. So loop, so that is also the instruction of the program what we have written. And next we have move r0, sum. So that is also the instruction of the program what we have written. And lastly we have 2 more. So return and end. So if you observe return, so return gives you the information about where to go back, and end, it gives you the information about it is the end of the text, it is the end of the program. So that information is conveyed to the assembler using end, and it gives you the start. So start is nothing but the address of the machine instruction after completion of the assembler program. So after the completion of all the instructions, the execution, the loader has to start execute. So that execution will start from the machine instructions. As I said before, these will not be executed. These are only the instructions which gives information to the assembler about where to place and what data needs to be loaded. So this is about the assembly language program for this code. So after this, you need to understand how the execution happens. So we discussed about the assembler directives. So what is the function of the assembler directives? What we have used in this program. Other than this, there are several other directives. So that we will see later whenever it occurs in the program. Now in this case, after observing the use usage of the assembler directives, we need to understand how the program is gets executed. Okay, in order to understand that, let us consider assembly and program execution. Okay, let us keep this as the reference code in order to understand assembly and program execution. Yes, so now if you consider the program execution, we know that in order to execute any program, it should be in the form of ones and zeros, and that function of converting the high level language into the machine level language is done by the assembler. Yes, after that, once the program is ready, so before that, okay, before execution, so what are the things that happens, that also we will discuss, and once the program is ready, so how to load that into the memory and how to execute, that also we will discuss. Now if you consider the program execution, we have already discussed the program execution in the first module, but there we have not discussed it at the level of assembly language. Instead of that, we just considered whatever the instruction we have in the source program, and we saw there will be two phases of execution. So one is instruction fetching, the other one is instruction execution. So instruction and fetching and execute cycles will be there, two phases will be there, and each and every instruction will be fetched, and after that, so it will be executed. So that is what we discussed. Okay, depending on the operations, okay, which are written in the program, the processor performs the operation and passes the control back to it may be due to the input devices, or it may be to the output devices, depending on, okay, whatever the code we have. So after discussing the execution, okay, with reference to the high level language, now we are going to discuss the execution with respect to the assembly language program. Okay, so first initially what happens, so before the program gets executed, initially the assembler, okay, will substitute all the names and the operation with their, okay, values, and along with the, so by substituting or replacing the names with the values, it also does the replacement of the constants. If the memory is to be reserved, okay, it will reserve the memory, and using this data word command, if you want to substitute constant, you can substitute. Okay, all these things will be carried out, so before the execution. Okay, so what are the operations that the assembler performs? Assembler, okay, replaces the symbols denoting the operations and, okay, the data with their equivalent values. After replacing, it will also assign the memory. As I said, okay, if you consider, okay, origin 100, it is going to assign the starting address for the instructions, machine instructions as 100. It assigns addresses to the data blocks as well as the instruction. After assigning the address, if the constants, okay, is to be written, so using the data word, okay, as the assembler directive, it is going to assign values to the constants. And after that, after assigning the constant value, if we want to reserve any memory for the program, okay, then it is going to reserve the memory. After doing all this, okay, it is going to start execution. Before that, so replacing name, so is a very, very important task for the assembler. So if we consider, okay, the directive or the instruction sum EQU 200, so in this case it is very easy, it is very straightforward. So we have sum EQU 200, therefore, so 200 will be directly assigned to sum. Wherever we encounter sum, so it is going to be replaced as 200. But if you consider, okay, the other labels, for example start and loop, okay, in this case it is very difficult to, okay, find out the values equivalent to this start and loop. So if the assembler has to find out what is the value of the start and what is the value of the loop, value is nothing but the memory address. If it has to be found, then it has to keep track of the object program. So if while each and every, okay, instruction is written, it has to keep track of the conversion from the high level language to machine level language, and it should note the address, okay, it should store the address where these instructions are stored. Therefore, so if you observe the program, start is at 100 and the loop is at 1, 1, 12. So if these values are to be replaced by the assembler, it need to keep track of the machine instructions. And sometimes in some cases, so the address will not be available like this. Meaning is, if you consider the program execution, if you have a branch which is after the execution of certain instruction, meaning is, so forward branch we say, so we have BGTZ loop, or if you consider this program itself, we have branch greater than 0 loop. Instead of this, so let us assume branch greater than 0, we have some loop 1, and loop 1 is present after this instruction somewhere in, let us assume it is at the 150th location, loop 1. So in this case, while executing, it will not be knowing, so what is this operand. So where is that operand? So since loop 1 is present after certain number of instructions, so it will not be knowing what is the value for this loop 1, so that it replaces that loop 1 with that value. So in this case, the assembler will be having a type of assembler, so which is called as 2-pass assembler. So whenever the assembler passes through this assembler code, it is going to scan the code and it is going to generate a table which is called as symbol table. So if it is one pass, it is very difficult, as I said. So in this case, if loop 1 is to be replaced at the first pass itself, then it will not be knowing. So it do not know where is loop 1 and do not know what is the value of the loop 1. So in this case, it is required to make use of 2-pass assembler, wherein 2-pass assembler, so in the first pass it is going to generate the value for all the symbols and the labels. It is going to generate and it is going to record it in the symbol table, and in the second pass the assignment will be done. Wherever it has to assign. Say for example, sum, here we have sum and it is 200. So initially it will store it as sum 200, and for each and every instruction it is going to have a conversion, or it is going to have a symbol table entry, and the replacement, as I said, sum here we have, so it is not going to be replaced as 200 in the first pass itself. In the second pass, that sum will be replaced as 200. So such an assembler is called as 2-pass assembler. So in this way, assembly level language program, so he will be converted into object program, that is machine level language program. And once the machine level language program or the object program is ready, then so we need to store that into the memory, because usually object program, whatever we get after the assembler performs or translates from source to object program, that object program will be present in the magnetic disk, and we have to move that magnetic disk, the contents which is present in the magnetic disk into the memory. So in order to do so, we require the input output operations that we will discuss in the next part. So now since we need to load that into the memory, actually we have another utility program system software that is present in the system, so that is called as loader. So this program loads the object program from the magnetic disk into the memory. So there are several operations need to be carried out, input output operations. All those things will be taken care by the loader. Loader is going to load the program, object program, from the magnetic disk into the memory. So once the object program is ready, is available in the memory, the processor starts execution. So once the execution starts, so depending on the data which is already assigned, so all the object program instructions will be executed. And after execution, if you have any errors, so that can be found by the user easily. And if you have any programming error, so in the syntax, okay, if there are any errors, so that will be, okay, given as syntax error, so before the compilation itself. So you will be knowing what are the errors you have. So if there are no errors, if the program is error free, so it will go up to the last and it will produce the results which are required. And if there are some errors other than, okay, the programming errors, so then that will be, okay, indicated by another system software that is present in the, okay, system, that is debugger. So using debugger we can detect if there are any others, okay, other than the syntax errors and logical errors. So logical errors has to be identified by the user, okay, or the programmer. Yes, so debugger function, okay, using debugger, user or the programmer can, okay, stop the execution of the object program in between, and he can check for the results, okay. He can inspect what are the contents of the different registers and what are the contents of the memory location, so that the execution, okay, or the program is, okay, is correct or not. In order to check, okay, the program is correct or not, he can stop at any point of time and he can verify the contents of the registers, okay. Yes, so this is about the assembly and program execution. And after this, so as I said, we are going to replace these labels, okay, and the data using the numbers. So number representation is very, very important, okay, and we know that numbers can be represented easily, okay, if you use integers. But when we consider the machine level language, we know that all these integers must be converted into the binary numbers. So if you want to represent the number directly using the binary representation, you can do, or we have other number representations like BCD we have and hexadecimal we have, and in many of the computers they make use of hexadecimal, okay, form of representing the numbers. So now let us, okay, see the number representation. Number representation. Yes, so we can use binary, okay, you can use BCD or you can use hexadecimal. So we are not going to use BCD. Why? Because so half of the numbers, okay, so the half in the sense if we consider 4-bit, okay, then the numbers that comes under BCD also comes under hexadecimal. So therefore instead of using BCD, you can make use of binary or hexadecimal. But even the integer numbers, okay, can also be used. But you need to indicate, okay, for example, if you are moving a data, say some 89, okay, into some register R0. So let us assume, okay, we are moving data 89 into register R0. If this is to be represented, okay, using 8-bit binary, then how do we represent 89? If you have 8 bits, okay, so since we have 89, so nearest is 64, okay, so let me B0, B1, B2, B3, B4, B5, B6, B7. So here its equivalent is 2, 4, 8, 16, then 32, 64, 128. Okay, let me shift because B0 value is not 2. I'm very sorry. So B0 is 1. 3, 4, 5, 6, 7. Okay, B0 to B7. Yes, so 89. Okay, so 64 you need to consider. This should be 0, and next 64 plus 32, it exceeds 90. So this should be 0. 64 plus 16. 64 plus 16 is 74. Okay, plus 6, 80. So this needs to be 1. So next we have 9. Okay, 8 plus 1. Yes, so if you want to use binary, okay, representation, then hash, okay, 0 1 0 1 1 0 0 1 comma R0. But you need to, okay, use some symbols so that, okay, it can be conveyed to the, okay, assemblers that it is a binary number. In order to do so, we make use of percentage, okay, so symbol to indicate that it is a binary number, okay. And if you are using hexadecimal, so how to use hexadecimal numbers? You have to group these into 4 bits each, and you need to represent the numbers, okay. And if you want to convey that this is hexadecimal, we make use of dollar symbol, okay. And so this is 5, 0 1 0 1 is 5, and this is 9, okay, comma R0. So this is how we use the numbers, okay, for the conveying the information in assembler. You can make use of integers, you can make use of binary, you can make use of hexadecimal numbers, okay, when you want to represent the numbers, okay, in case of assembly level language program, okay.